Good day and welcome to Calculus in the PM. My goodness. Anyways, I'm your host, Mr. Sandelica, and hot dog, we got another sight day here. Oh good, they're going away from us. I was worried that maybe they knew the fire alarm was going to be pulled in 10 seconds. That scared something out of me. Yeah, anyways, back to this. First of all, 3.2, revisited, I said. Now when I say 3.2, that's the previous section, right? That's the definition of a derivative, 3.2, 3.1. Remember the definition of a derivative? Now here's what I want to say. Evaluate the following expression using the simplest method possible. State the reason why you can use a shortcut. Now, taking a look at this expression, what does that look like to you? Thinking back to 3.1 and 3.2. It's the derivative of what function? What would
2x minus 2x? No, 2x cubed minus 2x.
Let's just think of, now this is not quite the definition of the derivative like x plus h, this is at a point, a plus h, right? Think back to this, it's the slope formula, right? And you're thinking this. This would be like 2a plus h, right? 2a cubed, right? Okay. Now, I'm going to just, what is the definition of the derivative at a point? Or x plus h notation, just tell me this. Just tell me what the definition of a derivative, either at a point or at a general point x.
Also the slope of the tangent line as a specific.
So we just call it f of x plus h minus f of x. Now it's really no different. Oh, I got that disappearing. Okay, now it's back on. There's a glitch in my software. When I use the eraser, sometimes it comes up like that and starts erasing. Anyways, that's the definition of the derivative, the general definition. If it was at a point, there's a philosophical difference here. We'd say it's an actual number, a, there. But this looks like the definition of the derivative at a point. What do you think your f of x was? It's easiest to look at the tail end, isn't it? 2x cubed, right? And the other one is 2x cubed with 3 plus h, or a plus h plugged into it. Eh? So knowing that, and that this is the definition of a derivative, right? Would you actually want to work this out? How do you do a derivative easier if it's just 2x cubed?
4x.
How do you do it easier though?
3
3 times 2 is 6. X squared. 6x squared. And what is the point that you want it, or what is the domain value that you want? At 3. So So you could do this, right? 9 times 6, 54. I can tell you, you could do it the long way if I said, must use the definition of the derivative to do this. You could do it, but it would take a while to cube those things up, right? And you might make a mistake. Now, my point is that you're going to come across multiple choice questions, almost guaranteed on the exam. And they will give you limits that look like this. And you might get sucked in and start doing this limit, which you can do, but it'll take you at least 2 minutes. If you recognize right away, hey, that's the definition of the derivative, you could just do a shortcut. What is the derivative of? It's of 2x cubed, and then I plug in my 3. Do you see, rather than doing that, if you're allowed, if it's just a multiple choice question, they don't care how you do it. And actually, they're probably, the whole point of the question is to recognize, definition of a derivative at a point. And you skip right down to that. You wouldn't be expected to do this. Do you follow that? So that's just something to be aware of. If I explicitly ask you to use the definition of a derivative, you must, okay? How about this? Theorem 1, though this is from the previous section here, differentiability. Implies continuity. Okay, that's from the previous section over here. And I said we'd get back to it, and now we're getting back to it. If f has a derivative at some value a, so 3, 2, whatever, then f is continuous at that point. It's a must. Okay. So example. Here's this piecewise function here. Let f be the piecewise function above. Which of the following statements are true? Now, what does this look like? What's this limit part look like? Looks like the definition of a derivative, doesn't it? From the left side. Okay. So, from the left side, you're allowed to use this equation portion, right? Because we're talking about 1. Right? 1 from the left side. The derivative from the left. Can you take the derivative from the left? No. It's not continuous. There's a jump there. So that one can't be true. Okay? And if you tried doing it, you come up with a wacky value that doesn't make sense. How about from the right side? Can you do the derivative from the right side? Only from the right side. Why, though, can you do the derivative from the right side? It includes this 1 here. It's x is greater than or equal to. That's what's important.
Doesn't the limit exist?
Okay. Question about the limit.
Doesn't the limit exist as 0 to negative? I mean, from the right side to 0.
Now, we're talking, and this is the other day where I made a mistake too. The limit for the function itself
Exists,
does, but not the derivative. What I'm talking about well, I'll just draw a rough sketch here. -5. Okay? Right? This one, oh. Okay. Agreed with this kind of picture here. I'm not worried about other details. Okay. Anyways, from the left, what you're saying is true. The limit for the function f of x as you approach 1 from the left does exist. That's true. And from the right, it does exist. They're two different values, so therefore a jump discontinuity. But the derivative implies that you have to take the secant line, the slope, as you approach this direction, to f of 1 in this case. And that will be different each time because I'm just drawing in different. It doesn't exist on this side. Okay, that's different. And I know where the confusion is because I did too. Now, if this left limit doesn't exist and this right limit does exist, does the derivative exist? No. I could see some students sort of mistakenly thinking it might, because don't be tempted. I hate showing mistakes, but I will. If you just think, oh yeah, the derivative of this is 3. If it was just that equation. The derivative of this is just 3. It's the same slope. And the way I drew it here, same slope. I drew them parallel, right? That's true, but it does not exist at that point 1 because it's not continuous there.
Is it vertical?
It's infinite. It makes no sense, actually, because you can't hone in on one value. It's undefined, we would say. So, to be differentiable, if you could do a derivative, it means it must be continuous at that spot. Otherwise, the derivative does not exist. Okay. An intermediate value theorem for derivatives. And I throw this in here just because the product rule, there isn't a lot to it. So going back to this, the intermediate value theorem, if A and B are any 2 points on an interval between a set of numbers, which is differentiable, then f prime, the derivative, takes on every value between the derivative at A and the derivative at B. F prime of A and F prime of B. In other words, though, let's translate this. Not every function can be a derivative. A derivative must have the intermediate value property. Huh? Come again. Well, let's take a look at this. You read through this, it might make some sense, but we got to think about this more, is why I'm saying, huh, come again. A differentiable function. So that implies continuous and differential. Y equals f of x has the following values for the derivative. The derivative at -1 is equal to -1, and the derivative at 1 is equal to 1, which could be a graph of the derivative. Well, you take a look. At -1, do I have a value of -1? So, yep, that's good. At +1, I have a value of 1. That's good, right? Does this one pass the first check? This does too. Oh, sorry. 1 and 1, -1, yeah. This works, this works. That condition is met in both pictures. But, intermediate value theorem. If you have derivatives, and I think you're thinking this through, that's good.
Isn't that the derivative? Isn't that 0?
Isn't it?
So,
No, I'm not asking you to find the derivative of these. What I'm asking you to say is this a possible function that could be is this a graph of a derivative? I'm telling you, the derivative values are these, given here. Oh, like, if I take the derivative, like, you know, if I had x squared as my function, and I said the derivative is 2x, right? And then I graphed it. It would look like this. I'm giving you the graph of the derivative, possibly. Now, knowing that by the intermediate value theorem, this is what we're saying. A derivative must have this intermediate value property, meaning for a derivative to be differentiable, it's got to be continuous and differentiable at every spot. Then the derivative takes on every value in between. Now, in between here and here, does the derivative take on every value in between here? Yes. So it's does it take on every value in between here and here? Nope, and I didn't mean to make a symbol there. Okay. This one cannot be a derivative because it's not a continuous function. It jumps. This could be. We don't have to know what the function was. It's just asked, what could this be? Yeah. This could be a and this is not possible. It's not continuous. It doesn't hit all the values in between those 2 points. And that's just and that's because it said it was a differentiable function originally. Okay? Now, we don't know anything about that function. We could have had, and I'll show you an example. I really don't care. Maybe jot in a quick graph underneath here. Now, what if I said 1 and negative 1 here, or I mean, negative 1, negative 1. 1 and 1. Same condition that I had above, right? Now this could be, I don't care what it is, it could be, I just made one up. This passes the test. It takes on every value in between and some beyond that, right? So this could also be. We don't know anything about F prime other than 1 and 1 and negative 1 and negative 1. This could be 2. As long as it's continuous in between and it includes the values in between here and here, right? That's all that matters. It could go beyond it. I just threw in a sketch willy-nilly though, like it's nothing. Okay? So the derivative will have this intermediate value theorem. It'll take on all the values in between. It'll have some consequences we get to later. Now, as usual, I want to review, and it was brought up, every time we do this product rule, we're actually doing a limit. We know the definition of the derivative, limit of h approaching 0 for the slope formula, f of x plus h minus f of x all over h. And a description of the derivative, as Zach had brought up earlier, someone from the middle bench, all the way along, I don't care who. Description of the derivative. What is it really? It's a formula that gives you what? Slope of the tangent line to some point that you might be interested on a curve, possibly, right? Okay. Every time we use this rule, we're avoiding using that limit notation, though. It still is. And we're finding formulas for the slope of the tangent line. Find the derivative of each function using the property rule. Simplify your results. Okay. I'm not going to be too hung up on simplify right now. However, I'm going to just rewrite this. Now, I have this color-coded on my screen just so that we could see something here. Now, y equals. I'm going to color code with, I got to be careful because I'm not good with colors. I'm going to memorize my colors now. Blue, I'll use 3x squared. 2x, 4 minus 4x. Now, before this, if you were given this on Friday, you would have multiplied these out and then did the derivative, right? Which actually isn't that bad in this case, and it's probably just as quick. It's when you get bigger monsters, though, that you really want to use this rule. So, it says to do the derivative of this function, it's not a composite function, right? It's a product. This times this, right? So, I'll say dy by dx. Y prime means the same thing as dy by dx, derivative. I'm going to give myself a bit of space. I need some light bit of space. Now, how do we read this rule? Think of first function, green as second function. The rule says if you're doing the derivative of this, take the derivative of the first function, leave the second one alone, as it originally was. So the derivative of the first function, 3x squared, 6x. The second one, don't touch a thing. Now, this adding sign, the addition sign is built into it. Then I got to put 3x squared. The first thing left alone, the derivative of the second thing. So the first thing left alone is 3x squared, as you mentioned. Second thing, derivative, I've got two chunks to it, but 8. X cubed minus 12x. Great. Now, I'm not going to worry about simplifying.
You just solve it.
You could simplify it. But if you were asked to evaluate it, why would you? I just, like if you're saying find the derivative of x equals 2, just plug the 2 in right there. You're probably better at arithmetic than simplifying. It's less time. Now, the derivative of two or more portions of a function. You just extend this rule basically. If you got f, g, and h, first, second, and third thing, you notice it starts the same way? Derivative of the first thing, leave the other things alone. Derivative, well, the first thing left alone, derivative of the second thing, leave the third thing alone. You're just sort of moving that through. First two things left alone, derivative of the third thing. Yeah. Now this one here too wouldn't be that bad to multiply out. It's an option. But if you had brackets with a lot of things, like if it was trinomial terms and stuff inside there, you definitely wouldn't want to multiply it out. Let's try this one here. Use the product rule to find. Okay. I'm just going to underline, this will be my green, this will be my red. Okay. F prime of negative 1. So first I need the expression, then I'll plug in my negative 1. So let's go with this. F prime of x. I'm applying this rule, which is derivative of the first thing, so 3x squared. Leave the other things alone. So meaning 1 minus 2x. 3x minus 1. Left them alone. The addition sign is built into the equation. Now, I leave the first thing alone, so it's x cubed. Derivative of the second thing, I could see when I run out of space. Where's my x cubed? Oh, derivative of 1 is 0, but then minus 2x, the derivative there is negative 2. And that's it. No x left. Third thing left alone. So I'm on this portion of the rule. I did it. Check, check. Now, derivative of the last thing, leave the first two things alone. Yep. I can't write that fast, young man. That's cool. Oh. And then 3x minus 1. The derivative is just the number 3. Now, I would not advise you to simplify anything on that, because we just have to evaluate. Use the product rule to determine f prime at negative 1. This is pretty simple arithmetic, negative 1 cubed and stuff like that. You just put it in here. And I'll drop the color scheme. Whatever, I'll just move it up. 3 times 1, negative 1 squared, so 3. Negative 1? Yeah. So negative 2 plus 1 plus 2, yeah, so 3. Negative 1. So negative 3, 4. No. Yeah, negative 4, yeah. Okay. Just plugging in negative 1 everywhere. Then minus. Well, no, I'm going to put it as plus, and then I'll put negative 1. The negative 2 can't change. It's a constant. And then negative 4. Of course. Let me see here. Apparently it's negative 53. I trust you. You're welcome. Oh, it's 9 times negative 4. Yeah.
Minus 36, minus 8, minus 9. 56.
Yep, negative 36, minus 8. Yep, 53, negative. Now what does that negative 53 give us? Because we're going to get a tangent line.
Like the slope.
Yeah, slope, because we plugged it into that formula that gives us the slope of the tangent line. It's called the derivative. Good, talking in circles. So, in order to find the line, though, we need a y value that corresponds with it. Through the point, negative 1 comma f of negative 1. Can you just plug this in here? In your head? Probably.
It will be 12.
Minus or positive.
Because there's two negatives. which
Yep.
are like each of
Good. Okay, you thought it through. It is 12. Okay. I have it worked out. It's 12. So I'm just going to write this down. Negative 1, 12. Okay. So then all I need is y minus 12
equal to negative 53 bracket x plus 4.
Okay, x minus negative 1 is really x plus 4. I don't know why I used, I guess I used the blue. Oh, what the heck did I say x plus 4 for? Yeah, I know. I don't know, I was thinking of something else as I was talking. Okay, there you go. That's an equation. Equation. That's all there is to it, though. Now, I don't have a heck of a lot today to add in. We'll try this. Right? I said to try this with me. 23. So, this is really abstract though. Suppose u and v are functions that are differentiable. We just don't know what they are. They could be like 3x cubed plus 5 is u, and 2x cubed minus x squared is v. You don't have to know that. All you have to know is how to apply this rule. This means do the derivative with respect to some variable x in there. Okay, I don't know what they are, but u and v, how do you do this? You do the derivative of the first thing. We just call it u prime. Leave the second thing alone. U and v are the first two things. Plus the first thing you left alone, v prime. Now I think you were getting ahead and doing at x equals 0. We've got, it says here, negative 3. I'm plugging it in from here. And v at 0 is negative 1.
3 plus 13.
And then u at 0 is 5. U prime, or no, v prime is 2. It's just arithmetic now.
13
10
plus 3.
plus 3 is 13. Y'all good with that? Now that's, in order to do questions like 24, A and D, apply the rule.
13.
Now what did I do?
13.
Why did I write that down? I don't know. I just, incomplete. 13. You know what, I was going to put 3 plus 10 down there. Yeah. I do know what I was going to do. Sorry. I've been making absent-minded errors a lot. So really what is this? This is just, what is the rule? Derivative of the first thing. Leave the second thing alone. Leave the first thing alone. Derivative of the second thing right there. That's what we did there, right? And then just plug in the numbers from a chart or whatever. Okay? This is your assignment. And I know some people complain all the time. Yes. Okay.